Advanced Concepts of Manual 224 for FAO. Yesterday, Dr. Eloisa Caldas, she presented on her session 1 for environmental fate of pesticides in soil, water, and water sediment systems. Today, Dr. Caldas is going to move, well, she started session 2 yesterday, so she'll continue with session 2, where she just started talking about sampling, sample preparation analysis, efficiency of extraction, stability of residues topic. And she's going to be presenting from now and for about another hour and a half, where we'll have another break, and then she'll continue with the topic. It's likely we're going to finish this topic a little early today, like we did yesterday, where we'll have some time for questions and answers. And then we'll likely be able to move a little early into session 3. So with that, I would like to hand it over to Dr. Caldas again to continue where she left off in yesterday's session. Thank you.
Thank you, Jason. Good morning, everyone. And someone needs to allow me to share my presentation. I'm not allowed to share my presentation yet. Someone has to allow it.
Guido, por favor, ¿le permites a la doctora compartir su presentación? Gracias.
Listo ya.
Yes, now I can. Thank you. So good morning, everyone. Let's start another morning. Oh, wait a minute. Okay, and today we will continue talking about the section 2. Yesterday we introduced the final about 30 minutes of the day. Yesterday we introduced some points about mainly about sampling, which is done in the field. So for those who are going to do a supervised trial in the field, or for those who are revising and evaluating supervised trials conducted by others. So we went through the main points about what should be considered when you sample a crop in the field. So I mentioned the Codex Alimentaris document. They stand 229, the link is there. And just to remind you that all the presentations will be available to everyone at the end of the week. So Veronica will send you everything. So you should look at that document if you are interested. And here just saying that you have to balance. The Codex document, it tells you the minimum amount of units or weight that you should sample in the field. And these figures here just show you that as many units you take, of course, the lower variability you're going to find in the composite sample or among the individual units, but you have to balance between enough unit samples with the capacity of bringing that sample from the field to the lab, and also the capacity of the lab to deal with that amount of sample. So that's why the Codex document, it's important, because it gives you the minimum unit number and the weight in case of the crop is has a big unit weight. For example, watermelon, you can bring to the lab 20 apples, but you cannot bring to the lab 10 watermelons. So that's why for watermelons, for big crops, it's the weight actually that will tell you how much you should sample and how much you should bring to the lab. And this restriction you really in the who is running the experiment in the field never try, and if you are evaluating a study who did that, you have to disregard it. You never the sample size should never be done, sample size reduction should never be done in the field. So if supervised trial is the person responsible for collecting the sample and send it to the lab should not really try to reduce the sample size in the field. For example, you should never accept a trial where, for example, they cut the watermelon in the field and just send a part of that watermelon to the lab. This is not acceptable, because as soon as you cut the sample, you really expose the surface of the crop to degradation. And during the whole process, you have to do everything you can to guarantee the integrity of the analytical sample of the residue, because what you want to analyze in the lab should reflect the residues that were in the crop when the crop was harvested. So that's something that you should not do, and you should not accept when you are evaluating the trial. And there is a Codex document for that, that's saying specifically about it, and also in the topic 3.4 of the manual. So, okay, now I think we finished yesterday with this slide, really emphasizing that what we should do to preserve the integrity of the sample. And I mentioned that you should, for example, process the sample frozen. Some people use dry ice, but you can also put the sample in the freeze before you process it, because then you will prevent the degradation of the sample during sample processing when the sample is which would happen more if you have the sample at room temperature. So if you decrease this the temperature of the sample, you prevent in a large amount the degradation of the pesticide. Remembering that nowadays, for the last many years now, all the pesticides are they degrade very rapidly. So the biggest actually challenge we have in the lab is to control the degradation of the standard. For example, we keep our standards as -20, but they do degrade very quickly. So it's not in the past where you have the OCs, the organochloride compounds persistent, that you could leave them. They were persistent in the lab, even at -20, and then you don't have to worry about it. Nowadays, it's a fight. Yes, you have to renew your analytical standards. You cannot use them if your laboratory is accredited according to the ISO 17025. They check for the validity of the standards and of the analytical standards, and the validity, it's very rarely higher than 1 year, sorry. And you should not use that analytical standard. So what I want to mean is that the pesticides that are used in agriculture today, they are not persistent, they degrade very rapidly, so you have to do everything to keep its integrity, and of course use valid analytical standards. So this is the field part of the supervised trial. And then the sample was correctly sampled and then arrived in the laboratory. I think Sorry, I changed these slides yesterday. Okay, when the arrive in the laboratory, you have to validate. Oh, I know what's happening. Sorry, I have to do something here because this is supposed to be, sorry. Yes, because that's the text that I was looking for is behind this table here. So I have to do that. Okay, now it's okay. Because that table should appear later on, and that cross here belongs to that table, but we can go with that. That's the information that I was looking for. Okay, the analytical method, first of all, ideally, all the laboratories, and actually when you evaluate the at national level and at GMPR, the study has to be in GLP. That means good laboratory practice. And that goes for field and laboratory work. And for laboratory work, most of the laboratories are now accredited according to ISO 17025. The last version of the ISO was in 2017, sorry. Before was 2005. I don't know how much of you are familiar with that good laboratory practice for analytical laboratories. In any case, ideally, the laboratory should be accredited, and which guarantee actually the registrability of all the results that are produced by that laboratory. The 17025 doesn't tell you how you should validate your method. It doesn't tell you anything about it. Just tell you how you should keep everything documented so you can prove that the analytical standards were valid, the analytical balance was calibrated. Every instrument that you use in the laboratory was calibrated. The temperature in the laboratory is controlled. The temperature in the freezer is controlled. All the people who are doing the analysis are well trained. So this is all part of the ISO 17025. So the ISO does not tell you how to validate a method, so that you should know how to validate a method, or the company who sent the laboratory who is running, who is analyzing the sample for that specific study should know that. And the method should determine all the analytes, including the residue definition, mainly for enforcement. I mean, mainly for enforcement because, as I mentioned before already, the biggest difficulty with analyzing the compounds, including the residue definition for dietary risk assessment, is the availability of analytical standards. It's very rare. For example, in my laboratory, which is accredited, I only have commercial metabolites, the major metabolites that are commercially available, which are included in the residue definition for enforcement. I don't have any metabolite, analytical standard for metabolite that are included in the residue definition for dietary intake, because those are very specific ones. Normally, the companies synthesize those compounds for their studies, for their the metabolism studies. So, so it's very difficult to have that. But for enforcement, you should look, the companies, when they provide the data package to GMPR or to national authorities, before they develop a method, they should know already what should be the residue definition. So they can include the analytes that are included in the residue definition in the method. There were times where actually there was a change in the residue definition during the peer review, the periodic review process at GMPR, and then the company did not provide analytical method that include that residue definition. So we cannot, because for dietary intake, I'm talking about dietary intake, actually, if you don't have that, you cannot do a dietary intake assessment. And if you cannot do dietary intake assessment, you cannot recommend an MRL. So both things, we're going to see about dietary intake. That will be basically the last talk of this week. But already talking about it, we have to talk about it before. So the company should know what is expected to be the residue definition for both enforcement and the dietary intake. Because if they don't analyze the samples for the compounds that are included in both residue definition, we cannot evaluate the compound correctly. So we just don't estimate maximum residue levels and don't recommend maximum residue level. So we should be aware that to recommend the maximum residue level, actually for the Codex Alimentaris, at the final process for the Codex Alimentaris to turn the recommendation in Codex MRLs, we have to show that at the CCPR, it will, the CCPR needs to have the result of the dietary risk assessment to really turn their MRL into our recommendation into maximum residue levels, Codex maximum residue levels. So we cannot separate both enforcement for dietary intake. So this maybe for those of you in which this is not clear, it will become more clear later on. And generally, we try to use multi-residue methods because in a monitoring laboratory, you cannot have specific methods. We're going to talk about specific cases where you cannot include the analytes into a multi-residue method. And those compounds actually, normally they are not analyzed in the laboratory because it's too much work. So normally we expect that the compounds basically included in the residue definition for enforcement could be analyzed into multi-residue method. So specific methods are not recommended. So, but in some cases there is no other way. So you have to use specific methods for that compounds because due to different physical chemical properties, that compound cannot be included in the multi-residue methods. So in the analytical method description, it should include the portion of the sample that was analyzed. Sometimes they analyze, for example, for crops that have inedible skin, inedible peel, for example, watermelon. Let's go back to the watermelon again. Sometimes they analyze the skin, the peel, and the pulp separately. They report that value, and then they calculate it based on the weight of the pulp in relation to the skin. They express the residue in terms of the total fruit. But why this is important? Because for dietary risk assessment, it's important to have the residue in the pulp because that's what we eat. Sometimes we don't have that information, and that is a problem. We're going to talk about it later on. But some trials, it has both results. The peel, three different results for each trial. The peel, the pulp and the residues in the total fruit. But the portion of the sample that was analyzed should be clearly speaking, written. And another some kinds, for example, rice, you can have rice as the way it's collecting the sample. You can have rice that is the outer part was taken out. You can have polished rice. So this has to be very clear which residue that sample is related to. The extraction and cleanup procedure needs to be specified. It's not written here, but of course the method for detection in almost all cases for multi-residue methods, they are chromatographic methods. And lately, I mean, the last 15 years, most of the methods are by LC-MS or GC-MS. So of course, the method used, the chromatographic method used should be really clear, specified. And then actually we don't, because in the laboratory for you have to do a full validation. And the full validation include more than actually we have for the data provided and actually what we actually evaluated from the residue methods. But normally the methods should be, the sample should be fortified at least 3 different levels, but sometimes there are more than that, and then at least with 3 replicates for you to estimate the recovery and the repeatability of the method. And then from that validation table, which include basically, my validation table include much more than that, but the validation table that we normally get from the companies include the fortification level, the recovery that were obtained, and the standard deviation of replicate samples. And you should have at least 3 replicate samples for you to derive a percent of a relative standard deviation. So for those of you who are not very familiar with these analytical procedures, you may ask some questions later on. And then you have also to define the limit of quantification for the method. And it can be different for each crop, but normally it does not vary too much. And not required, but sometimes the company also derive a limit of detection. In general, the limit of quantification is defined as the lowest level that had a good recovery and good repeatability. And you're going to see that table that I'm supposed to show on the top of this slide. And also, you have to show the stability of the residues during sample processing, during the sample storage. Sorry, it should be a storage here, not processing. And this is a table that I got from the manual, where the minimal criteria for the method performance are written here. So you have the recovery here. It depends on the level that you fortified your sample. For very, very low levels, you can accept even lower recoveries, up to from 50 to 120%. And the relative standard deviation could be as high as 35%. As you increase the levels of fortification, and then you are more restricted related to the recovery and also related to the repeatability. Most methods are in the range of 0.01 or at lower range like that. And then normally in our current procedure, we look for a repeatability that is not higher than 20% and a recovery that ranges from 70 to 120%. And it has to be clear that this recovery and repeatability is for each fortification level. So the companies sometimes they do that. They blend all the results from all the fortification levels in only one. You cannot do that because you're going to define the LOQ, the limit of quantification, based on the performance of the lowest fortification level, which nowadays it's very rare to see a LOQ higher than 0.01. More and more, we are seeing LOQs below 0.01, sometimes up to 0.05. That's why I cross these last two lines here, because those LOQs and those, you can see the fortification levels at that done of the method performed at higher level, but you normally today you don't accept LOQs at level higher than 0.1. This was kind of normal in the past. We had evaluated some trials, some analytical methods a long time ago, where the LOQ, that is the mean, the lowest level of that the performance of the method was evaluated lower than 0.01, but not anymore. In the table, in the validation table, you may find the fortification levels up to 1 milligram per kilogram. Higher, it's really not very important, but LOQs today, with the state-of-art equipments, you don't expect LOQs. You expect actually that the analytical methods perform very well at 0.01 milligram per kilogram at least. So the companies should look for that to validate the methods at the lowest concentration possible. It's very common to find it 0.05, 0.02, 0.002, 0.005. So in that range, or in that range, but not in this range here. And should the company validate the method for each single crop? For example, let's see that the company, the gap, the label, the compound is registered for many fruits and vegetables, leafy vegetables, tuber vegetables, different cereals, oil seeds. Should we, many different fruits, many different vegetables, should the company validate the methods separated for each one of the crops for which the compound has registration to be used? Not necessarily. That's why, for example, we accept kind of representative crops for commodities with high water content, for example. So you can actually validate the method for one of those. You don't have to validate the method for apples, pears, apricot, cherries, peaches, bananas. So you just choose one of those crops which have high water content and do the validation, and then you can extrapolate. You can assume that the method will perform well for the other compounds as well. So it's normally you have the company select some of those crops from this category, high water content, and then validate the method for some of those crops, not necessarily for all those crops. And then you have high acid content and high water content. So that goes for citrus fruits, small berries, small fruits and berries, and there are a lot of fruits that are included in that category. Why this high acid content is important? Because you may have some degradation, acid degradation of the pesticide due to the acidity of the crop. So that's why in this case, this high acid content crops are separated here. So the company may choose to normally validate the method for orange. It should cover all these commodity category. And for example, another is high oil content and very low water content. So tree nuts, oil seed, high oil content and intermediate water content. It's not necessarily, sorry. It's not necessary to really validate for everyone. Cereals, normally you do a validation for 1 or 2 different cereals, for 1 or 2 dry beans. And there are some difficult and unique commodities. For example, hops, cocoa, coffee, spices. So some crops are very difficult because they have they are very complex matrices that can cause matrix effect. There are ways to go around these matrix effects, and normally the validation, the sample is analyzed against a in-matrix standard curve. So normally in the lab, we use a standard curve in solvent. But in our laboratory, for example, no matter what we analyze, we always use an in-matrix standard curve. And that is the term from the matrix effect experiment. And that goes mainly for those very difficult crops. Hops is very difficult to analyze. Coffee, very difficult as well. So there are difficult crops. But in any case, the company or you in a laboratory that is intending to provide data to the GMPR or to national level should really try to prove that the method that you have or the methods that you have can be applied to any crop for which the compound will be registered. I'm going to give you how, so the analytical method is an important, very important part of the data package. And I'm going to give you an example. And that here I'm saying for plant commodities, but you have to also look for animal commodities. Normally, I don't show it here, but you have to validate the method for meat, liver, kidney. Normally you use the same method which should be applied to liver and kidney, and then milk, and then eggs. You don't have to validate for example, cow meat and hen's meat. So normally if you make the validation for hen's commodity, it should apply for tissue, poultry tissues. It should apply also for mammalian tissues. But of course you have to have a different, you have to validate for milk and for eggs separately. And if you don't have analytical methods that the performance of the method was shown, you cannot go forward with the recommendation. And this was the compound that I evaluate this year at the GMPR, so I'm just bringing it here already. The report was not yet released, I think, but I'm going to bring you this firsthand. Okay, metalaxyl and metalaxyl M. Metalaxyl, it's a racemic mixture that is it's mixture of both stereoisomers R and S, and metalaxyl M, which was introduced in the market later on. The company could actually synthesize one of the isomers, only the R isomer, which they call it metalaxyl M. But metalaxyl, which is the racemic mixture, it's still used in many countries. Still registered in many countries, although most of the registration are for metalaxyl M. But when you go to the laboratory, normally you don't have a chromatographic column that separate the two isomers. So what you have at the end, which could be GC or ALC, it's metalaxyl, because you cannot separate the two isomers. So the residue definition is the same for both metalaxyl and metalaxyl M. And now the recommendation applies to both compounds, because in the laboratory, when the sample arrives, you don't know which compound was applied. The companies, when the company submit the data package, the company knows exactly which product was applied. If it was metalaxyl, which is a racemic mixture, or if it was metalaxyl M. But we in the lab, we don't know. So I cannot make a residue definition that would difference between the two, because the analytical method does not do that. So the residue definition is metalaxyl, period. And the point that I have here, that was a problem that we faced in this year, was that the residue definition for metalaxyl and metalaxyl M, because it's the same, for compliance with animal commodities, is the sum of metalaxyl and both enantiomers, because you cannot separate them, and the metabolites, and that is include two metabolites. I don't show you here the metabolism pathway, but two metabolites are really found at higher concentration, at highest level, even in some animal commodities at higher concentration than the metalaxyl itself. So even for enforcement, those two metabolites, M3 and M8, in the free and conjugated form, are included in the residue definition for enforcement for animal commodities for metalaxyl, period. However, the analytical method for animal commodities, it's based on the common moiety method. That means the metalaxyl for animal commodities, they do an extraction and they heat under reflux. Is a very old method, but they haven't changed it. And then they submitted the sample to a heavy hydrolysis step, and everything, all the metabolites and the compounds are converted to this common moiety method, the 2,6-dimethylamine. And that's exactly what I measure at the end. It can be measured by GC, it can be measured by LC, MS, but actually everything is converted to this common moiety. However, the analytical method was only validated, that means they only fortified the sample with metalaxyl. They did not they did fortify the sample with M3 and M8, but the recovery was very low. So you cannot say that the method was validated for M3 and M8. So currently, and this, I mean, this year, there is no methods, analytical method validated that includes all the compounds that are in the residue definition for enforcement. I don't even get here in the residue definition for dietary intake for animal commodities because it contains 5 metabolites. So in this case, we estimate what is left for the cow to ingest, but we could not make any recommendation for animal commodities because there is no valid analytical method, validated analytical method. So what I want to point out here that if there is no validated method to analyze all the compounds that are included in residue definition for enforcement, you cannot make a recommendation. And that was the case here specifically for metalaxyl and metalaxyl. So this was a fresh case, very fresh case. You're going to see this in the 2021 report. So that's what we call enforcement analytical method. You have to have, the company has to provide a method that could be enforced in the laboratory. Because national government, not the GMPR, of course, but national government need to enforce the maximum residue levels, either the MRLs that were established at national levels or the MRLs, the Codex MRLs. So we need enforcement method. For that case of metalaxyl and metalaxyl M, there was no enforcement method that include all the compounds for enforcement. So, so what is the advantage? Normally, you have multi-residue methods. For example, for those of you who are in a way work in the laboratory, you've heard about the Quetcher's method, which became available in the beginning of this century, already in 2003, almost 20 years ago. Actually, the Quetcher's method did not introduce anything very new. It just put together some tools that were available already, and it just made the extraction easy with a lower amount of sample of solvent as well. That's why it's called quick, cheap, although it's not very cheap, quick, efficient, cheap. The S is sustainable, I think. I really forgot the other, what means the other letters here. But the Quetcher's method is very spread. It can analyze a large range of pesticides in a large range of crops. So that's really the optimal enforcement method that could be applied, because the laboratory, it does not want to have one method for fruits and vegetables, and another method for grains, and another method for oilseeds, and another method for legumes. The best would be to have one method for all the crops, validated, of course, you have to validate them separately, and that would cover the analysis of many, many pesticides. There are methods today that are validated for over 400 pesticides. In my laboratory, our scope is 103, 104 pesticides. And I use a slightly different method from Quetcher's, because Quetcher's use acetonitrile for extraction, and I use ethyl acetate. But actually it's dispersive cleanup as well, so it's very close. So if you have a very complex, and also ideally you should have a simple enforcement method, because a simple enforcement method will make that the laboratory could analyze more samples. And if you have difficult residues or difficult methods that involves, for example, acid step, too many cleanup steps, in some cases, for example, in the laboratory, for some other samples, I don't even need a cleanup step. And you see, even for pesticides and for fruits, for example, some methods that do not include a cleanup step. So you just extract, dilute, and shoot in the equipment. That's the best you desire for in a laboratory. So if you have difficult methods to analyze difficult residues, for example, there are some pesticides that are very difficult to analyze because they are too polar. For example, glyphosate, glufosinate, paraquat, diquat. They are very nasty, difficult residues. sometimes you have to adjust your method to analyze those difficult residues, and some laboratories cannot really, if the methods are very difficult and they do not perform well, they cannot verify the compliance with the MRL. And that's the thing that I mentioned before. If many metabolites are included in the residue definition for dietary intake, you just cannot do a proper dietary intake assessment in a routine base because you don't have an analytical standard. And that is not a problem with developing countries in Latin America. This is a problem everywhere, because unless the company, sometimes it happens that you can ask the company to provide you with the metabolites, and then you can do that. But most of the metabolites nowadays, because as I mentioned, the residue definition are getting more and more complicated, you just don't have those analytes, and you have to validate the method for each metabolite. If you don't have this analytical standard, how are you going to validate the method? So that's a problem. But there are non-specific analytical methods, and the classical example are the thiocarbamates. I don't know if you have the experience of the thiocarbamate analysis. Normally in a routine, in many laboratories, they just don't analyze the thiocarbamate because because of the physical chemical characteristics of the thiocarbamate. Some are polymers, they are not water soluble, or they are not soluble in any solvent. For example, mancozeb, mechiran, and propineb, they are just polymers. They don't have, they are not soluble in organic solvents, so you cannot include them in the Quaternion method, for example, in a multi-residue method. So you have to analyze them separately. And after the herbicides, glyphosate and 2,4-D, which are the herbicides most used in the world, the fungicides are the class of pesticide most used in the world, and among the fungicides, the thiocarbamates are the most used in the world, and they are normally detected with higher frequency in the crops. But the problem is that to analyze thiocarbamate, you need a specific method. There is no way around it, and that's why the residue definition, and it's also based on a common moiety. And the common moiety is the CS2. So you don't analyze in the method used worldwide in the monitoring laboratory, you don't analyze each one of there are many others. Here I just put the ones that are registered in Brazil, just for example. But there are others. There may be registered somewhere else, but normally, and among the thiocarbamates, the most sold and used around the world is mancozeb. And you can see that all those thiocarbamate, they have this common moiety here, the CS2, and that's what you analyze afterward. So the thiocarbamate you need a specific method, and the method is based on a common moiety, like the metalaxyl M and metalaxyl for animal commodities. Here, the common moiety is CS2, which is produced after acid hydrolysis. So you submit the sample to acid hydrolysis, and then you produce one part of the molecule, and you produce, for example, for Zira and for mancozeb as well, for mechiran, you produce for each molecule of Zira, which actually is not in this list. For each molecule of Zira, you produce 2 molecules of CS2. This CS2 can be analyzed by spectrophotometry by spectrophotometry. and by GC, ECD, different detectors, GC, ECD, FPD, or mass spec. But all have the same problem. You don't know exactly which compound was applied to the field, because all the compounds give rise to a common moiety, which is the CHS2. And in the laboratory, because we have been analyzing, we have been dealing with dithiocarbamate for the last 20 years. We even developed a specific methods to analyze CS2 by spectrophotometry. But we are working in the laboratory to develop a method, an LCMS method, to analyze specifically mancozeb and mechiran. At least we would know what we are measuring, not based on a common moiety method. The problem with that method, in addition for you not to know which compound was applied, that's why the residue definition is based on the CHS2, because it reflects the limitation of the method. The method measures CS2, so the residue definition was really linked to the capacity of what method of what the method could analyze. The method analyzed CS2. So in this case, the residue definition is directly linked to the analytical method. And so dithiocarbamate has three major issues. First, you cannot, it's a common moiety method. You cannot tell exactly in a monitoring laboratory which compound was applied to the field. And third, you have some crops that you don't even analyze it because it gives false positive, like the brassica and the onions. It just, because those crops have sulfur compounds, and when you hit the sample, you produce also CS2. So after all, you measure CS2, but not necessarily that CS2 came from the application of dithiocarbamate. So those crops, for example, broccoli, cabbage, onion, those are the three major examples. In the laboratory, we don't even analyze it. And if you see results from monitoring data, you cannot tell that is not false positive. And you see many monitoring data from I think from USA as well. I think US dithiocarbamates are not allowed to be used in USA anymore. But in Europe, even in Brazil, you have results for dithiocarbamates for crops that gives false positive. So you should be aware of that. So that is a non-specific analytical method that is very important for a very important group of pesticides. And the efficiency of the extraction of the analytical method, which does not apply actually to dithiocarbamate, it's not really required. Yeah, we don't stop going forward in analyze the analytical method if the efficiency of extraction is not provided. Because the real efficiency of extraction data comes from the metabolism samples that were generated in the metabolism studies. So some companies, they know that, though, so they keep the samples from the metabolism studies, which were C14. So they know exactly how much you should extract from, because they measure with C14, and then they compare the result with a method which is used routinely. And from that, they estimate the extraction efficiency. Because here in the validation, there is no other way to do that. What you do, you fortify a blank sample. That means a sample that was not treated. That is, we call a blank sample or a control sample. You fortify with the pesticide that you are validating the method for, and you normally fortify, leave it for some minutes, and then you extract it. So it's not encouraged residues. So in these minutes, for systemic pesticide, for example, there is no time for the pesticide really integrate inside the crop. But that's the way it's done all over the world. So, but in the metabolism analysis, actually, you have the samples that were treated and with a compound that was labeled with C14. So this is the real concentration. So you compare with when you analyze the sample with the monitoring method. And here you see for pear, for fodder, maize fodder, cucumber, information for cucumber at different concentration, animal commodities, goat meat, milk, and you have different extraction efficiency. You have very poor extraction efficiency for goat milk. You can see here 24% of the residues were actually extracted using that method. So that means that that method is not good for goat milk. And for pear, it's acceptable. For cucumber, a very high variability at lower concentration. So this is it's information that is desirable, but it's not required. Okay. So sometimes we have it, sometimes we don't have it. But if you don't have it, you just go forward without it. So we rely on the validation, normal validation method, because that's what actually the laboratories, they do. They don't have C14 samples from metabolism study in a normal laboratory. So you have to be realistic and really accept what the laboratory does. There are some cases where some issues can affect the analytical recovery. You hope for a good recovery, but in some cases, this cannot happen. I'm just going to give one case of glufosinate, which is an herbicide with the structure very close to glyphosate, which is a very, is the most used herbicide, the most used pesticide worldwide is glyphosate. And glyphosate has a very similar structure, and we have transgenic crops that are resistant to glyphosate and to glufosinate. The problem is that during the sample extraction, the sample actually, because you have the enzyme, the transgenic sample, converts the compound to, this actually occurs during the sample processing, to acetylglufosinate, which is this compound. So during the method, you have an acetylation here at this point, here in the amino group. So after all, you're not going to recover as much of the glufosinate, because some of the glufosinate was actually converted by the crop enzyme to the acetylated form. So just show that there are some issues for some crops and for some pesticide that you cannot control. Just a specific case for transgenic crop. In our laboratory, we do analyze glufosinate and glyphosate and the metabolite of glyphosate AMPA using in water only, using a specific column. So those are very polar compounds. They are not included in most of the multi-residue methods. That's why it's not very common to see residue data for those herbicides. Herbicides in general, they are very difficult to analyze. But we do analyze glyphosate and glufosinate in water and the AMPA, which is the main metabolite but we have a separate method for that. Actually, we have a separate equipment currently we have a LCMS just to analyze those 3 compounds because it needs a specific column. The LOQ is very, very low. But just to show that in this case, it's because the crop is transgenic. So you're never going to get, with the normal method, a good recovery. So you have just to live with the recovered around 50 and 60%, because that's real life. And the last topic in the evaluation, in the section of analytical method, is the stability of the residues in the sample processing and storage, actually in the deep frozen storage. I should actually change here because we're gonna talk about processing later. It's kind of together here, but we should not mix them together here. Let me correct that. It probably is together in the program, but it's going to be a different topic. I wonder. Okay. So normally what happens? The sample is harvested. The sample is collected in the field, sent to the laboratory. But normally the laboratory does not analyze the sample right away. In some cases, because see, those are completely 2 different facilities. One and in a GLP, you have the study director for the field section of the study, and you have another study director for the analytical analysis of the sample. So those are 2 different things, and sometimes they are kilometers apart. And the sample is sent to the laboratory, and normally it stays there in the freezer before it's really analyzed. So what the company has to prove is that there was no degradation of the pesticide during that time that the sample was stored in the freezer, waiting to be analyzed. So the company has to prove that there was no significant changes in the residue concentration, because again, what you analyze to be the number of the residue trial should reflect what was in the sample when it was collected. So if the sample actually is analyzed within 30 days, yeah, for some reason, the analysis of the sample was very quick. It was collected in the field, correctly sent to the laboratory, processed, and then the sample was stored in the sample in the freeze at -20 for 30 days. And then these studies of stability are not necessary, but normally it's very rare that occurs. Normally the sample stays at least 1 year. It's very normal that the sample stays in the freeze 1 year, over 1 year before it actually analyzed. It is actually analyzed. And even in this case, you have to go to the physical chemical properties to show that the samples really, they have stability, they don't degrade very rapidly, that you can accept not to have a stability study in the study report. But you have to, otherwise, which is in most cases, you have to conduct stability studies. And again, you don't have to conduct stability study for each crop that the compound was registered. You can choose crops from each category. It's the same rationale that we had for the analytical method validation. So you choose 1 or 2 crops that have high water content, high acid content, high oil content, high protein content, high starch content. So you really don't have to do for each crop that the compound is registered for. And you as evaluator, has, after you look at the storage stability studies, because you look at the storage stability studies before you go to the residue trials. So you look at the storage stability study and see, okay, those residues are stable up to 6 months, up to 1 year. All right. So the residue trials, the real residue trials, the sample should not be stored for a period which is higher than the stability study was conducted for. So if the stability study proves that the residues are stable up to 6 months only, during the residue trials, the samples cannot be stored over 6 months, because it was proven that the residue, the pesticide was only stable. It could be stable for more than 6 months, but it was not proven. So if you check those things, you should be able to make the following statement. I just took that statement for my Metalaxio report. It was demonstrated the sample storage stability covers the sample storage period using the supervised trials considered by the current meeting. So you need to have that statement, because if you have a residue trial that the sample was storage for, let's see that for the storage was storage for longer than the storage stability study was conducted, you just have to disregard that residue trial. And in the evaluation, you have a sample table like that. So normally the company fortified the sample at different levels, sometimes 10 milligrams per kilogram, but normally at very lower level. I got this example here, but sometimes 0.1 milligram per kilogram. This is a very high level. And analyze the sample by a method that was reported, a validated method, of course. Analyze the sample as soon as the sample was fortified, which is 0.2. And here you have the method recovery. And then you analyze which is kind of within the acceptable recovery rate. So the method was validated. And then you analyze the sample at 0 day, you get those values. You have a mean percentage of, in this case, 0 days, what was there. And then you analyze after 4 months, 0.24 months, that is about some days, 1 month, 2 months, 5 months, 8 months, up to 10 days. And you see that there was a kind of increasing in what was recovered here. So up to 1 month, this is an example where actually there was a degradation of the residue in the freeze, because here, see, after 8 months, you could only recover 37% of the residues, but the method recovery at that day was also very low. But for example, here, after 5 months, you have a recovery rate around 70%, and you only could find about 44% of the residues that were there in the first place. So this is a problematic pesticide, I don't know which one, but what you want to see here is that the percent remaining stays between 70 and 100%. So at least 70%. And here, this compound. So for these specific compounds, the company should analyze the sample as soon as it gets to the laboratory, because there was a degradation of the residue.
Eloisa, you have about 5 minutes before break.
Okay, good. We just finished this talk. Oh, see? Perfect.
That's perfect.
That's perfect. And you have to, when you evaluating a study, you have to look at the design of the study, the storage, where the sample was stored, if the sample was homogenized or just chopped. Normally it's homogenized. If actually the sample could have, because you have to analyze the stability of all the compounds that are included in the residue definition, not only the parent compound. Because again, you have to make sure that what you measure in the sample for enforcement, you have to make sure that you analyze all the compounds included in the enforcement. Sometimes the company conduct this study with encouraged residue. That means they sample a crop in the field, which was treated, and just follow how the residues stays over a period of time. Normally, they do conduct those studies at least 6 months, but it's very usual. It's very normal to see up to 24 months, because it's normal that the samples could be stored for a long time. So you have to see the procedural recovery. You see here in this day, here the procedural recovery was very low. And you have to check actually the storage temperature. Yeah. So you have to look at the of the study report to see actually if although they say -20, if the freezer control temperature was really at -20. And in this table, you should have, sometimes the company, they adjust the recovery for the analytical method recovery. They should never do that, never. Because that's the real life. So the procedure recover, it's inherent to the method. But here clearly you see that these days, the same method, but these days here, the recovery of the method was not very good. And this is normal to have in the laboratory. Sometimes I say to my friends that do not really have real experience, when they see 68% of recovery, they go crazy. Oh, it's lower than 70. But I say, sometimes you have to live with that, because one of the replicates was 68%, but the other one was 74, the other one was 70. So in average is around 70%. So this is normal. Laboratory life is not easy. So the analytical chemists really, it's not trivial. So that's it. We're going to have a 15 minutes break, Jason?
I think it's a 10-minute break.
In the program is 15. No?
The program I'm
Oh,
looking
no,
at
it's 10 minutes break. Okay.
Yes.
10
And
minutes
then
break.
following the break, are you going to continue with another presentation, or should we go for question and answers?
Yes, I'd like to go for questions of this topic before we move to the next section.
Okay, well, we'll use this time during the break to look through the chat room, and then also hopefully people can use this break time to submit some questions for us. Okay. Thank you.
Good.
Okay.
Thank you.
Thank you very much. And we're going to be playing the video again that we had yesterday for the break time. So please enjoy that while you're typing up your questions for Dr. Caldas. Thank you.
Nos encontramos en las instalaciones del ensayo 12318-19 S01, que corresponde al ensayo de determinación de residuos de la combinación espinetoram-piña. Nos encontramos con Germán Lochamín, que es el director ejecutivo de Asopiña, y el gerente general de Agroeden, que es la empresa donde estamos haciendo los ensayos.
Productores formales en el país, para llamarse exportadores deben cumplir con sistemas de gestión, certificaciones que avalen un producto inocuo. Las certificaciones, estamos hablando de buenas prácticas agrícolas o Global Gap, que es el requerimiento mínimo para poder exportar. Todas nos exigen el cumplimiento de directrices con respecto a LMRs y a listas de productos que podemos usar. Partiendo de eso, podemos decir que el cumplimiento de los LMRs establecidos en países destino es uno de los principales retos. ¿El por qué? Porque, como ustedes sabrán, hay muchas moléculas a las cuales sus LMRs se están reduciendo y muchas otras que dejan de estar autorizadas para su uso, y eso nos reduce a nosotros como como productores de cultivos menores, nos reduce la posibilidad de tener moléculas y así evitar resistencia de plagas y enfermedades. Entonces, son muy importantes. Nosotros no tenemos otros medios por los cuales podamos primero permitir que cultivos como la piña en este caso tengan su interpretación de nuevas moléculas. Para nosotros ha sido muy complejo entrar a algunos mercados en los cuales no hay nuevas moléculas, y que en otros mercados con mucha más investigación, hablamos de Europa, Estados Unidos, de moléculas donde ya se permiten, ya se manejan, pero nosotros no podemos enviar o mantener nuevas moléculas porque en sí el producto no está ampliado para piña. Los LMRs no existen, entonces eso se vuelve muy complejo y nos ralentiza el avance que como sector productivo necesitamos, ¿no? Que es algo muy dinámico. Salen moléculas, tenemos resistencia de plagas, tenemos que siempre estar innovando y buscando evitar la resistencia de plagas. Entonces, el tema de que la fundación apoye con estas investigaciones son muy relevantes, ¿no? Sí, es importante no solo apoyar desde nuestra parte productiva, sino procurar que esto se profundice y lo hagamos mucho más. La limitación de uso de moléculas, por así decirlo, medianamente antiguas, nos ha limitado mucho, y hay que tomar en cuenta que todo lo que son cambios climáticos, ahora mismo aquí en el país tenemos mucha variación de clima, no podemos definir, ya no tenemos definidos nuestros veranos, nuestros inviernos, tenemos poblaciones flotantes de plagas que son estacionarias, que tienen un comportamiento errático para lo que nosotros manejábamos, y eso va a involucrar retos muy importantes ligados al tema de desarrollo, investigación, uso de nuevas moléculas, y por ende es muy importante el trabajar mancomunadamente con todas las organizaciones para poder establecer estos LMRs y poder usarlos en nuestros cultivos.
So I think that the break is finished, and we would like to now move on to a question and answer session from Dr. Caldas, and Adriana will be assisting us with the reading the questions that have been submitted through the chat box. If time permits, we might allow for just people to raise their hands for the Q&A, but I think we have plenty of questions just in the chat box now to try this. And this is and after we do this, this would wrap up our session on sampling and sample preparation, and we will be moving along to the selection of supervised trials for the estimation of the STMRs, etc. After we have the Q&A session, which we will budget about 30 minutes for, I think. But if it goes longer, we can try longer, and it'll be up to Dr. Caldas to determine how many questions she'd like to take before she moves to the next session. Okay, thank you, Adriana. Can you please take it over now for the Q&A session?
Yes, Jason, thank you. So the first question is from Carla Arrieta.
Methods. And would you like to take any questions toward the end of today, or do you want to wait until you're completely done with this session tomorrow to take the questions?
I think it's better to wait until tomorrow, because the whole issue is very related. So we start with the section today and see how it goes. Okay? Maybe if people, yeah, let's see how it goes here.
Okay.
I really would like to add additional information to this section, because I think we will have time. So so let's see how it goes, because I really want to update this presentation, mainly the last part of this presentation, to really bring additional information to the workshop.
Okay, thank you.
Okay, I think it's yes. Let me just a minute. I'm going to close this door here. I went to close all the doors because I'm not alone anymore. So, and then the translator does not complain of outside noise. Okay, now we're going to the key. We would say that everything that we've seen up to now, it's kind of background information for what we're going to see next. Because the heart of the whole thing is the supervised trials. Although we cannot evaluate supervised trials without having all the information that we have been talking so far. So in the evaluation document, after analytical methods and stability of residues, you're going to see the big gap table, which is the use pattern. And then you're going to see the supervised trials. Many of the supervised trials that are submitted to GMPR, and I believe that I don't work at national, here in Brazil at the national authority, that may happen too. Many of the trials, they submit, but they know that they are not according to GAP, but they submit anyway. And in some cases, those trials can even be helpful for us to decide on some issues. For example, when some trials are conducted twice the gap, we're going to talk about that. And then the first thing you have to see is that if the trials are independent supervised trials, because you find, for example, you find many trials that were conducted in France, and some trials that were, two trials that were conducted in the same region of France. So you really have to go into the report and check the timing, if there was the same region, but maybe in different places. And one issue that we're going to talk about here is the use of alternative gap. very important. When we should apply proportionality, and when we should crop grouping. Crop grouping is a key issue for minor crops. You all know about it. And the last year has been a key issue at GMPR. And finally, tomorrow probably, we're gonna make some examples using the OECD calculator, which is the statistical method for estimating maximum residue levels. Okay, use pattern. I think everybody here knows what use pattern is. It's based, I teach toxicology to my pharmacy students. So I used to say that the gap, the good agriculture practice is the good patient practice. In principle, the patient should not use a medicament, should use the medicament exactly how it's written in the label of the medicament. And I also make this comparison with the label of a medicament label with the label of a pesticide, because that's in the label where how the pesticide should be used in the field. So for them, it's a good comparison because they can relate with medicaments. So that's why. And this register use, it's approved at national level. And it's important to mention that we only evaluate pesticides at GMPR which have been registered at least one country. We had one compound this year that was only registered, I don't remember the name of the compound, but it was only registered in Ecuador. I will not remember this compound. Only in Ecuador. For some reason, the company decided to register its compound. It's a new compound at GMPR. And the company decided to start the registration process by registering the compound in Ecuador. And when it's registered, so it has a label. Because in the past, so this is standard. We only evaluate the compound if there is an approved label somewhere in the world. In the past, the companies, in some case, they had pressure. They had pressured the GMPR because they said, no, this is a pending label. Yes, but you know that a pending label can, for example, sometimes the company would say, no, this label will be approved by EPA very soon. But this very soon sometimes could take 1 year and the label would not be approved for some reason. Here in Brazil, sometimes there is a large delay from the time that the applicants require registration and the registration is approved. So in the past, we would kind of, the company, no, this label, that's going to be the gap. It's not approved yet, but it will be approved soon. So now for the last, I don't know how many years, we don't accept any pending label. Okay, only accept labels that were approved, really approved by the government. And as we have people from many countries, sometimes we have doubts. So because the company provides a label, and sometimes it's a translated label to English, and it's not really the original label. So we contact our friends in each country and say, is this compound was really registered? Because if it's not registered, we don't evaluate. We don't even look at the data. In the label, you all know, have information such as dose rate, number of application interval, post-harvest interval, which is the PHI, and many other information you all know, because regarding the safety of the pesticide and many other information, the pests that those pesticide controls, And one important issue here is the critical gap, because one pesticide can be registered in a country under different labels, and each label can indicate a different use. So you have one product and the label says up to 3 applications with a PHI of, I don't know, 10 days. And another label registered in the same country says up to 5 applications. And then which is the critical gap in that country? Is the gap the label that says that the compound can be applied up to 5 times? Sometimes because the interval, the application interval is too large, it may not affect the final residue, but sometimes it does. And also, for example, you can have a gap registered in France, another one in Spain, 2 different countries, or a pesticide that is registered in Spain, and I'll give you one example, and a pesticide that is registered in the United States. They have different gaps, different application, different modes of application, and one of those gaps will lead to the highest residue. Because you have to keep in mind what is the purpose of a Codex MRL, is facilitate trade. So if it is facilitate trade, the MRL should reflect the most critical use that will lead to the highest residue. Because if you establish an MRL based on the highest residue, every other gap that will be the residues that the other less critical uses will be within, below that maximum residue level, so that will be okay. And of course, there is a dietary risk assessment to show that the potential risk or no risk of that use. I have a good example that this will be more clear. So that's the critical gap, the use pattern leading to the highest residue. Normally, of course, the highest dose, number of applications, shortest retreatment interval, and shortest PHI. Yeah. In the past, we would not. Nowadays, we are very key in looking at the pre-treatment, the retreatment interval. Yes, what is the difference between in days between the first and the second application, the third application? What is that interval? So we are always in the last 5 or 6 years reporting that in every residue trial table in the report as well. And here's just one example, yeah, of a label. Most of you are familiar with that. So this is, I think it's metalaxyl as well. Yeah, I just got some information for my compound this year. And here, there was a question previously about having formulation with 2 pesticides. In this case, metalaxyl and mancozeb. This is a label from Chile. It's in Spain. It's in Spanish. You can see that. I'm pretty sure that is a label from Chile. And here this label can be used for the residue trials for metalaxyl and mancozeb as well. Yeah. And sometimes in this case, mancozeb is analyzed by a completely different method, but they could provide the data together if they want to. In this case, it's not very good because mancozeb is a diethylcarbamate, as I mentioned. You need a specific method. But when they have 2 compounds which can be analyzed by multi-residue methods, they use the same method, the same analytical method to analyze both compounds. So they get 2 results from the same work. It's the same application in the field, And then the same analytical methods, the same residue trials, the same analysis of the samples. So it's very useful for the company, and they can provide the same data package for the residue trial for 2 compounds. For the analytical method, this is not good for Mancozeb. But here you have all the crops, registered crops in Chile for these Ridomil Gold. That's the name of it's the WG formulation, concentration of the compounds in the formulation. And this is registered for these crops. There are other crops, ornamental crops that I did not include here, but potato, tomato, onions, and other samples. This would be a problem to enforce for Mancozeb, because I told you that onions, cabbage, cauliflower, and spinach, they are brassica, and they give false positive for Mancozeb. So this would be a difficult to enforce. And the dose that needs to be applied, and how it should be applied, the application interval, 7 to 10 days, the dilution of the compound, you can use up to 3 applications. And the critical gap here is 3 applications. If there is a trial where there was only 1 application, so that's not the critical one. Although the farmer can use 1 up to 3, it depends on the pest pressure. Yeah, sometimes you don't need to apply 3 applications. It's like a medicament for headache. You can use up to 6 to 3 times per day, but sometimes you use 1 time, that's fine. You don't need to use 3 times. The same here. So if a trial was conducted with the gap rate, the correct gap rate, but only 1 application was used, it is not according to the critical gap. So that's the critical gap, because for sure, unless you show that the last 2 applications really, the first 2 applications really does not add to the final residue, but then you have to show it, and then you can accept 1 or 2 applications instead of 3. But again, it's always case by case. That's why it's really an expert judgment, because sometimes, for example, the gap says up to 3 applications, and then the residue trials use 5 applications. Too much. You cannot apply proportionality to a number of applications, just to the rate. I'm going to explain later. So in that case, wow, the gap says 3 applications, but the residue trials were conducted with 5 applications. Are these 5 applications, this trial which was conducted with 5 applications according to gap? It depends. Because sometimes the 2 first application really does not impact the final residues, because the compound degraded very rapidly. After the first application, degrade very rapidly, and then you apply the second one, it degrades. Então, actually, what you see finally after the 5 applications, very similar to what you would see with 3 applications. And in this case, if you look at the GMPR reports, you're always going to see a statement like that. Although the trials were conducted with 5 applications, the meeting agreed that the 2 first applications do not contribute significantly, do not contribute to the final residues found in the crop. So we accept that trial. So you see, so you always have to look at the gap table to see all those parameters. But again, sometimes you have to use expert judgment. So that is the gap. And in this specific case, it has, let me take this here. The PHI, the período de carência, and it's different for each crop. For grapes, is 28 days. That means for grapes here, you can apply at a maximum of 4 application, with 14 days application between the applications. And you should harvest this sample 28 days after the last application. That's what the PHI means. And it's different for grapes, 28 days, for framboesa, 21 days. I don't know what mora is, but please translate that. For those 214, for spinach, I think 10 days, for chicoria, 8 days, and it depends. The PHI depends. And the PHI has to do with the, it's an agronomic recommendation to really protect the samples from the pest. It's not a number that comes up like that. So normally this is recommended by the company. The company finds what would be the best. It's like for the medicament as well. The company which produces the medicament finds what's the best way to use that medicament to treat that that effect, that disease, that whatever. And that's normally the company who actually provide that information, propose a registration label to the government. Here in Brazil, where we have 3 government bodies to register pesticide, IBAMA to look for environmental issues, Anvisa for human health issues, is the MAPA, the Ministry of Agriculture, who look at that label and that recommendation, use recommendations really to register the compound. And that is the supervised trials. So here in the evaluation, we have this big gap table. I didn't bring you one example here, which has all the crops for which there will be residue trials evaluated, and all the countries relevant for our evaluation, how those crops are registered in all the countries that are relevant for the evaluation. Okay, so that is the gap table. I think I'm going to include the gap table here in the next version of this presentation, so you could see how it looks like. And at the GMPR, we as evaluator, the company provide, I have to tell you one thing, the company provide the studies, and the companies provide also a monography, which contain the raw data. Why the monography provided by the company is important? Because it contains the table. They produce the tables, the gap tables, the metabolism tables, the environmental fate tables. They provide all the tables, but because then we don't have to make up the tables, because it's very hard to make up the tables. But what we have to do is to check every single number in those tables, metabolism, environmental fate, analytical method, compare if the numbers are corrected with the studies, because the company has to provide each study, the whole study, the PDF file of each study, and in addition to the monograph. So what I do as a GMPR evaluator, I start with the monograph from the table. That's where I start. And for example, for the gap table, and the company should provide all the labels, the original labels that are included in their gap table. So what I have to do, and they provide the gap table, which the dose, which the crop, with the interval, retreatment interval. So what I have to do is to check every single table to see if the numbers provided by the company are the correct numbers. Sometimes they are not. Sometimes the labels are very complicated. For example, some EPA labels, they are very complicated to interpret. So, and that's why we always ask for help. For example, we have Michael, which works for the EPA and for the GMPR. And some labels from EPA, they are very complicated to explain sometimes, to interpret. So we ask Michael, who works at EPA, to help us with the interpretation with the EPA labels. And sometimes they are not in agreement with what the company provides. So we then change what the table provided by the company. So we do have to check every single label provided by the company. So this is very important because those tables are very long, sometimes 3-page tables, sometimes 30 labels that we have to check, but that's our job. So it's just to highlight that the work that we do for the GMPR, we start doing month before the GMPR. I normally start the GMPR, meetings are normally in September. We receive the information from the company by February, and I start work with the compounds in April, because I have to construct the evaluation of that compound and the appraisal of that compound. So we start very, very ahead of time. When we go to the meeting, we have both documents ready for discussion in the meeting, and during the meeting, they change version 1, version 2, version 3, version 4, and it's hard work. It's hard work because we don't accept everything that the company says. We have to check the original studies to check if everything is okay. Normally, most things are correct, but sometimes we find inconsistencies and we have to correct the monograph. So just for you to say. And here, the pesticides then are applied to crop according. No, animals here, I include the animals because some pesticides, also some insecticides, they may be applied directly to the animals as insecticides. According to specific conditions, intend to reflect commercial practice. Commercial practice is actually the gap. And the residues designed to reflect the intended pesticide use pattern, giving the highest residues matching the critical gap. Just repeating this. So this, to repeat these things, it's very normal that, for example, at GMPR, for most crops, we accept, for crops that are very important in international trade, for example, cereals, we cannot make any recommendation with less than 8 different numbers, 8 residue trials. And it's very common to have a very large variability of residues among the 8 residue trials, although they all use the same application frequency, application interval. The samples were all harvested at the same PHI. So that's what this graphic shows here. So you see a very large variability. You're going to see it later in some examples where you have, for a single crop using the same gap, results range from, I don't know here, below 0.5 to 2 milligram per kilogram. This is very common. That's why you need a minimum number of trials to derive a maximum residue levels. For some minor crops, we may accept a lower number of trials, but now with the crop grouping, we have other crops that can support those recommendations because the minor crops they are included in the crop groups. But as as higher are the numbers of residue trials, the best is our estimation of the maximum residue levels. Even the OECD calculator, when you have a very few data points there, it's going to give you a message that the estimation was not very good. We're going to make some examples of using the OECD calculator. You're going to see if you have too many numbers below the LQs, or you have too many, very few, a very low number of trials, the OECD calculator will give an error message. Sometimes you have to deal with that, but the minimum number of trials that the calculator will not going to complain is 8. Sometimes the company is not a requirement. It's not a GMPR requirement, and it may be a requirement by some national authorities, but it's not a requirement by GMPR. Some countries conduct what we call declining studies. Although the PHI is set by the gap, for example, 10 days, 14 days, it's good to know how the residues decline with the time. So sometimes we have residues that the samples are harvested at 0 day, and then at 3 days, and then at 6 days, 10 days, 14 days, 21 days, up to 28 days, although the PHI is 5 days or 6 days. But this information, these declining studies are very important to have an idea. If I can use, for example, a sample, if the PHI is 10, if the PHI is stable after 10 days, I may even use a study in which the sample was collected 14 days, for example, because we know from declining study that the residues are not expected to decline very much after a certain day. So declining studies, again, although not required, strictly required, they are very useful when we evaluate the trials. So why the results are so variable, even if the same gap, the same application, same if all the trials are conducted according to gap? Because you apply today here, and then it rains, the temperature is higher today, or it's lower today. Today it rains, so everything that you applied yesterday was washed out. So it depends. Here you apply with the gap, and then you apply in another city according to the same gap. You have to put those numbers together because they were all applied according to gap. That's why it's normal if you have a big countries like Brazil that the trials are conducted in different parts of Brazil, because you cannot derive a maximum residue level that would reflect the use only in one part of the country. It's like when you look at that globally, yes, you cannot, you want to reflect the most critical condition for the residue situation. So you want to have a recommendation that would cover all the other conditions in a country or in different countries, because of the different climates in one region from the other one, sometimes in the same country. So that's the main point here in this. And then you receive this residue trial table, and then you have to first decide which trials are valid, right? And then you go to the report of that trial and see if the trial was well designed, was well conducted, and well reported. So again, if the sample, if the trial was conducted according, if the equipment that applied the solution was calibrated, if the sample was collected correctly, if the sample was not cut in the field, if the sample reduction was not done in the field, if everything was correct and everything was well reported. You have to look if the trials are independent. Sometimes the trials were conducted in the same region, for example. I'm going to give the example of Brazil. And then in the gap, the residue trial table, it says Brazil, Minas Gerais. The same city, for example, I don't know, Uberaba in Minas Gerais, in Brazil. And I would say, no, 2 trials in the same city. Are they independent? If they were conducted at completely different time of the year, they are independent. But if you have 2 trials conducted in the same region, and it does not have to be in the same city, but very close together, during the same month, so they are not independent trials. So in this case, you have to choose one of the trials only. You cannot choose the 2 different trials, and the company is not very smart. It's a waste of money if the company conduct 2 trials in the same region at the same time. They are not independent trials. They are different plots of the same trial, and only one number will be chosen from that. Normally, we choose the highest number from those 2 plots. They are not different trials, they are different plots. And in this case, normally we don't consider independent as well if they have, if they are different varieties of, for example, apple. If you have 2 trials conducted side by side, different varieties of apple, they are not different trials. They are not independent. The only difference between those 2 trials is the variety of the apple. They are not independent. So you should choose only one of them. If, for example, you have 2 different formulations, apply side by side or very close together during the same time. They are not independent trials, just because there are 2 different formulations. I think there was a question about different formulation application. Normally, it's agreed that the formulation does not really have a great influence on the final residue found in the crop. So they are not independent trial. So the first thing you see are the trial validness, are the sample were storage during a period that it was shown in the storage stability study that they were stable. So you have to see everything. If the trial is valid, and then the second thing, if you have 2 different trials, 2 trials in the same region, the same country, are they independent? Because you cannot replicate the numbers if they are not independent. And then another issue that you may apply, you have always to look at trials according to gap. But sometimes you may have, let's say, if the gap is application rate of 0.1 kilogram of active ingredient per hectare. That's the gap rate. Apply up to 3 times at 0.1 kilogram per active ingredient per hectare and harvest at PHI of 20 days, for example. But the trial was conducted at 0.5 kilogram per hectare, very far away from the gap. The gap was 0.1. But let's see if the file was applied at 1.2. The gap was 0.1, but the trial was conducted with 1.2, 0.1, not 0.1, but 0.12. Can I consider that trial being at gap? Yes, because we accept a variability of plus or minus 25%. Let's say that if the PHI is 5 days, and then the sample was harvested at 4 days, is 4 days within the 25% of 5 days. 5 days, 25% of 5 days is what? Less than 1 day, right? Or a little bit higher than 1 day. So let's get a number that is easier. Let's say if the PHI is 4, but the sample was harvested at 3 days. 3 days is within 25% of 4, yes. So you can accept that trial. So with the PHI of 4, you can accept trials that were conducted at, samples were harvested at 3 days, and samples were harvested at up to 5 days. You can accept that because it's within the range of 25%. You cannot apply the 25% rule to both the rate and the PHI. You can only apply to the rate or to the PHI, because then you can underestimate the residue or overestimate the residue, which you also don't want to. So that gives a little bit of flexibility of evaluating the trial. And then you can apply the principle of proportionality. This principle of proportionality was actually started to be applied at GMPR. I will not say exactly the year, but maybe around, it was before 2010. Not when I started in 1997, but before 2010, that for sure. And at that time, we would not accept, for example, if a trial was conducted at a rate much higher than 25% of the rate, we would not accept, period. But then, again, to make the best use of the data, there was even a discussion at CCPR. Don't CCPR asked GMPR to consider assuming that there is a linearity between what is applied and what is found. If you apply more, you find more. So when the CCPR asked us to consider, can't you use the proportionality? For example, if the gap is 1, I'm going to use single numbers here at first, but then I'll give you additional information. If the gap is 1 and you apply 4 times more, if the gap is 1 and the residue is 1, but if the trial was conducted with 4 kilograms per hectare, can you derive what would be the residue at gap? So that is the proportionality. So it's the rate is applied from 0.3 to 4 times the critical gap, at lower gap, much lower rate than the gap, or much higher rate than the gap, you can adjust the residue that would be expected. Just doing a rule of 3, yes? At 4 kilograms per hectare, you find this residue level. How much would you expect if you if the trial would be run using 1 kilogram per hectare? 4 times less. So that is the principle of proportionality. Of course, when the CCPR suggests something, we evaluate scientifically that this is reasonable to apply. So it's not like CCPR told us to do, we would do it without really investigate that it's reasonable to do it. So this was investigated, so we evaluate many trials, comparing, and it was shown that within that range of only to the application rate, we could apply the proportionality principle. And that was good because we could make the best use of the data that was provided to us. So before we would disregard the trial, and then we start to use trials, applying the proportionality rule. So that was good. It was
Oh, it's
start from the CPR. Yes?
Oh, I'm sorry. You have just over 10 minutes left, and there are a couple questions that came in. Would you be willing to entertain those questions, or would you like to continue with your next slide? Is this a good time to
No,
break it?
I think if you have question at this moment, we can do that. Why not?
Okay, thank you. Adriana, maybe you can help with those.
Yes, there are questions from the previous section. So one was en español. Gracias a todos. Sí, perdón, gracias. A todos, gracias por su participación. Realmente increíble. Entre ayer y hoy, entre 70 y 100 personas. Muchas gracias, de una gran cantidad de países. Excelente. Lo que les quería avisar es que el último día queremos hacer una encuesta sobre el evento y algo muy importante que queremos es la recomendación sobre nuevos temas para nuevos entrenamientos. Eso es todo lo que tenía que decir para hoy. De nuevo, gracias por su participación. Ya son las 12:01. Entonces yo creo que podemos cerrar el evento de hoy. Muchas gracias, Eloisa, por favor. Claro que sí.
Okay. Bye bye, everyone. See you, everyone, tomorrow. Bye
Hasta
bye.
luego.
Bye.
Hasta luego.
Bye-bye.